So I will just share my screen so that we can get going. Confirm that you can see my slide. You can see my slide? Anyone?
Yes, Doctor, we can see.
Okay, thank you. So I'll put it in full screen. So here we go. Now, so this is the title of the talk. We will be using exploratory data analysis to explore some data later. But first of all, we'll go through a few concepts involved. So this is not, I wouldn't call it, it's by no means comprehensive. There's a lot more you can do on this. But since we have only 1 hour and we have the slides and the Python code to look at, we'll keep it brief and just cover a few concepts that are useful. So as mentioned by Henry, I'm Dr. James Katende from the Department of Mathematics at the University of Nairobi, and I will be taking you through this. So the key things we expect you to get from this is to understand what exploratory data analysis is, be able to identify some key statistical measures, visualizations, and ask some more questions after looking at them. And eventually we shall do a live demo using Python to illustrate some of the concepts we'll mention in the slides. And the slides and videos will be shared later at the end of probably sometime either today or tomorrow, as well as the code and the data used in the code. So EDA basically helps us to summarize data into the main characteristics, looking for patterns, finding outliers or unusually large or small values or anomalies that exist within the data. So it also gives us ideas on what kind of questions we can ask or what are the meaningful questions you can ask about the data. And sometimes you may need to use this to check some assumptions for any subsequent statistical analysis that you wish to do. So it's actually a very important step. It may not be conclusive in many cases, but it does shed some light on a number of things and can get you started on getting a grip on your data. So these are some of the, I've already mentioned this, it's basically some of the places where you can use exploratory data analysis to gain insights, clean your data, create new features in your data, generate questions on your data, and prepare your models for machine learning. We won't be doing any machine learning today. Today we are working with the basic statistics, showing the power that you have with basic statistics. Often we tout the machine learning as very important, which it is, but it's good not to forget about the basic statistics, which can help you get quite some insights out of your data without too much powerful techniques. So we will quickly look at the types of variables that we'll look at. The first one is a quantitative variable. Now, these are numerical variables and they come in two versions. You have a discrete variables, which are distinct values. Examples include the number of lights, number of passengers, and so on. So these are just values that take on distinct values, variables rather, that take on. Then there's continuous variables, and these can take on any value within a given range. So examples would be, in our case, what we shall look at: flight delay time, the distance traveled, and so on. The continuous variables can be further split into more categories, but we'll keep that out of the talk. You have interval data, you have scale data, and so on. But we'll leave that out for now. Then you have the qualitative variables. And these you can think of them as labels. They come in two versions as well. There's the nominal kind, where there's no inherent order. Things like names of cars, the name of an airline, the name of a city, that's a nominal. You can't really order them. The order may not make sense in general. Then you have the ordinal variables, which are also categories, but they have some inherent order in them. So one example here is customer satisfaction ratings, where you can rate them as low, medium, or high, depending on what you have. But then they are not numerical variables. In essence, they are categorical, though they have some inherent order in them. And you may not be able to measure the distance, the actual distance, say, between low and medium, or medium and high, or different. There might be more than one way to do that. So it's not objective, but there's still some inherent order. So the first type of statistics we'll compute will be measures of central tendency. These ones try to pick out the typical value in a data set. So the first measure is the mean, or what you may call the average. It has some advantages. It's quite convenient for further statistical calculations, and usually it's preferred. Where it makes sense, it's preferred for further statistical calculations. The problem it has is that it is quite sensitive to large, unusually large or small values, and these ones may skew the results. There are a couple of things you can do about that. We shall see later. Then we have a median, which simply splits the data into two equal parts, half on one end and the other half on the other end. It's not very sensitive to extreme values, and may not be quite amenable to further statistical analysis, but there are places where you can use it, and it has its use cases. The mode is the most frequently occurring value in a data set, and this may apply more to discrete values. So if, for instance, if you're counting the number of cars owned by people in a certain community, maybe some people may own 3, 4. So if 4 is the most frequently occurring value, then we call it the mode. So the measures of central tendency do not tell you everything about the data. At some point, we are interested in knowing the spread, how dispersed the data is. So for that, we bring in a few other measurements. The first one we look at is the interquartile range. This one simply gets the difference between the third quartile and the first quartile. Now, I didn't define those, but the third quartile is simply the value below which the 75% of the data is, and the first quartile, or Q1, is the value for which there's 25% of the data below that value. And in between the first quartile and the third quartile, there's 50% of the data in between there. So the difference between these two gives you a measure of how spread out the data is. And one advantage it has is it's resistant to outliers and may work well for skewed data that is skewed. We shall see examples of what we mean by skewed data. So the other one is variance. It also gives you a measure of the spread, how well spread out the data is. The only problem is that if you have very large values, it will be affected. It can be exaggerated if you have very large values, and also very small values can pull it down. The standard deviation is just the square root of the variance. The major advantage is it will now be in the same units as the data. And you can easily compare with the values within the data directly. The variance is the square of the units, and therefore sometimes we may not be able to use it directly until we compute the standard deviation, which is now in the same units as the values in the data. So the other thing that now the spread does not tell you anything about the shape as well. So the shape of the data can be covered in two parts. There's a skewness, which checks whether the data is symmetrical. So you can have right skewed data. For right skewed data, the tail extends to the right. And for left skewed data, the tail extends to the left. We shall see some diagrams on this. Then we have kurtosis, which measures the peakedness or flatness of the data. So look at if, again, we'll not compute this, but it's possible to visualize these two. The flatter distributions have a lower peak, and those with high kurtosis have a sharper peak. So here is some visualization for some of the ideas. So if you look at this first graph, this shows a right skewed data. Right skewed, the tail, it tails out here to the right. So you have most of the values are on the left side. There are a few values, extreme values on the right side. So this one is left skewed. It means most of the values are on the right side of the distribution, or on the larger values are more common than the smaller values. So if you look at the right skewed, the first one, the mean, this red line represents the mean value for the data, and it's because of these large values, the mean is pushed, or rather pulled, towards the large values. That's what we meant earlier on when we said it's sensitive to the outliers. Now the median is not as sensitive to outliers, so it has not been affected so much by these large values, and it's to the left of the mean. The situation is reversed here when you have left skewed data, but when you have symmetric data, the mean and the median are they lie at around the same point. So this would work for symmetrical distributions. Particularly, you could talk of a normal distribution or the T distribution. There are a few others, the Cauchy distribution, that are also symmetrical, and so on. So now still on visualization, the other way we can visualize data is by using bar charts. Here we check the number of flights by airline. And clearly you can see United Airlines seems to have the highest number of flights. We shall describe the data later, so you will get to know what this represents. But this is what a bar chart will look like. You can choose to have the bars as horizontal or vertical. I chose them as horizontal here because of the labels. The labels are a bit long, so if you try to put them on the x-axis, they will overlap, or you'd have to make them at a right angle, and that may not be as readable as horizontal labels. So it's just a matter of circumstance. You can make them vertical or horizontal. So the other visualization you can use is line plots. This can help you track trends over time. You can use this for time series. So here, this tracks the average monthly flight delays in minutes across the 1 year. And you can see the delays on average seem to be higher in the middle of the year and a little lower towards the end. So you can also visualize the spread using, these are not box plots. This first one is a histogram. The box plot is here, but these work well together because they bring out, the box plot brings out some information that you may not easily see here. So these extended values, extreme values are what you see appearing as dots here. This first value on the edge, the left edge of a red box normally represents the first quartile. The line in the middle represents the median. The right border of this red box lies at the third quartile. So this distance between or if you like, the width of this rectangle is actually the interquartile range. Then these bars have either will be at the maximum, or on this side it will be at the minimum point, either that or it will be at the point which is 1.5 times the interquartile range plus the lower quartile, whichever is nearer. So there are no outliers on this left side, but on the right-hand side, you have some outliers. So this point will be 1.5 times the interquartile range from the third quartile. So points that lie outside these bars, these two bars that you see at the end, are usually considered outliers, and sometimes maybe they may be replaced by other values or ignored completely, depending on what you want to do. And depending on your domain, sometimes you may extend these bars to more than 1.5 times the interquartile range. Then the histogram simply shows you the distribution. This one, it turns out that the departure is skewed to the right. So the smaller values are more common. So this again is just a histogram. So when it comes to the shape of the data, sometimes you may encounter what we call the multimodal. So you have two peaks within the histogram. So this is neither skewed to the right nor to the left. Neither is it symmetrical, but it is multimodal. So you end up with two peaks. So this just shows the distribution of the distance covered by the aeroplanes. And it appears to have two clusters. You have this one cluster that cover quite a long distance. Then there's these other clusters that cover from low to medium distances. So the next thing we look at are scatter plots. Scatter plots help you to check the relationship between two numerical variables. In this case, we are checking the relationship between the delay, arrivals delays and the departure delays. And it seems to make sense because the longer the departure delay is, the longer the arrival delay. There's some variation in the lower values, but towards for the larger values of the departure delay, there seems to be a fairly strong linear relationship between the time, the departure delay and the delay in arrival as well. So the other thing you can do is cross tabulations. In this case, we have destinations along the rows here. So these labels are for destinations. Then we have here for the columns, we have airports, the airports of origin, and then these are the destinations. So this simply gives you count. So for instance, this count at this point gives you the number of flights from this airport, EWR, to this destination. So this, usually when you do these cross tabulations, sometimes you might get missing values. The missing values may be because there are no flights maybe from this airport to this destination. For those ones that just replaced with 0. So this also can be useful. Now, if the labels are too many, sometimes it's quite hard to keep track of what is going on, but it gives you some idea of what you can do with the data. So it gives you counts. The same cross tabulations can be converted into bar charts. So this is viewed as a bar chart. So you have, in this case, you have the number of flights for each quarter. And this is done for every different airline. I think these are the airlines. So for each airline, you have the number of flights in each quarter. The blue one stands for the first quarter. This orange is the second quarter. The green is the third quarter, and the red is the fourth quarter. And across the board, it seems there are way more flights for every airline, almost every airline in the first quarter. Now, the only problem with this is if you have some really small values that are difficult to see. You can see like this. I don't know if you can see where my mouse is. I'm trying to point here. These are really small. You can't see them clearly. So what you can do with this is you can rescale, use the log scale on the y-axis. I think we can do this in the script when we are running the live demonstration, so that you see what happens, so that we can cure this problem. But then that works if all you're interested in is seeing the relative differences and not the actual values. So the other thing you can do is get pivot tables. So pivot tables get different combinations of two categorical variables. So in this case, we have the different airlines, and then we have the different airports. There are 3 airports, and then the airlines are many. So each entry here is supposed to be I think this was the average delay in departure for flights. So for instance, if you pick this point, the average delay for the departure is 31 minutes. So that's the Alaska Airlines, and the airport is EWR. On average, the delays are about 31 minutes. That is covering the whole year. You can now break this down into smaller time periods if that is of interest. So that brings us to the end of the discussion before we go to the live demonstration. Here we have some references, which a couple of golden oldies from 1977 and 1985, which I still consider relevant. Then we have some new ones, which are more recent. So if you want to, this one by Wesley McKinney is good for if you want to work with Python. If you want to work with R, this one by Hadley Wickham is more appropriate. So I don't know if there are any questions on this, or we can just go direct to the. We'll share the slides either today or tomorrow for all those who have registered. Do we have any questions, or do we just go to the demonstration now? So like I said, what we have done is by no means exhaustive. There are many more things you can do on exploratory data analysis, but we We're just giving a peek of what is possible, a sneak peek. So I suppose there are no questions, so we can now move to the live demonstration. So the data we shall be working with is from the US Bureau of Transportation, and shows the flights that depart from New York, all the flights departing from New York City in 2013. So I got this data from the NYC Flights 13 package in the R software. So all I did is I got it from the package, then I saved it as a CSV file and imported it into Google Colab. We shall be using Google Colab, which is it's free to use, and you can use it. You don't have to install anything on your machine. You just use it online. I will share the link to this. So here are some of the packages we'll use. Now, if you are new to Python, I would propose that you just focus on the output and how we interpret the output. It may not be possible to learn Python in this same talk and also explain everything. But when we run our short course in about 2 weeks, I think we will we'll be able to teach people more detail, both the statistical and machine learning side, as well as the coding. So we import some of the packages that we need. We need Pandas for handling the data frames, NumPy for some calculations, Matplotlib and Seaborn for the visualization. And I don't know if I used this at some point, but datetime for handling dates. So we can run that. Then I have my flights that are already as a CSV file. It's stored in a Google Drive. Can I confirm that I am audible? I've talked for a while. Need to know if I can be heard.
Yes, you're audible.
You're audible.
Thank you. So I've brought in the data. Or have I? I think so. Yeah, it is in. So this is the data. You can see it has a lot of variables. We have the year, month, and day. The year is 2013 because all these flights were in 2013. So there's no change. It's the only year that you will see there is 2013. This is a month. Month will run different values from 1 to 12, representing January to December. And then the day will just be the day of a month. So for instance, this one is the 1st of January, 2013. And there are more values. This is just the top 4 values, top 5 values. So there are all these variables. We have the departure time. That's the time the plane leaves. So observe how it is noted. Probably this should be converted to integer, but not a problem for us. So for instance, 5:17 a.m. is written as 517. That's how it's recorded. And then there's the scheduled departure time, again with the same format. They recorded 5:15 a.m. as 515. They use a 24-hour clock. So midnight will be recorded as 24. And the rest, as you know, the 24-hour clock. Now, this is the delay in departure. I think this was in minutes. Some will be negative, meaning they left before time. The negative values, I think, mean that the plane left earlier than scheduled. So the delay is recorded as negative. Then there's arrival time. Again, it's written in the 24-hour clock, but written just as a number. So 830 here means 8:30 a.m. Good idea. If you want it to make more sense, you have to convert this variable to an integer. So there's a scheduled arrival time and so on. There are all these variables, the delay in arrival, the name of the carrier, the flights, the tail number. I think this is like a registration number. There's the origin. These are the airports. I think there are 3 in total. The destinations are many, but the airports are only 3. The amount of time in the air, the distance covered, I think this covers the amount of time in the air. So 5 hours, 15 minutes, 5 hours, 29 minutes, 5 hours, 40 minutes. I'm not sure what this last one, maybe this time hour may have been the time. No, I'm not sure what these last 3 variables stand for. Let me not, a good way would be to go to R and look for this flight's data. They will have a description of these last 3 variables. But that tells you the data we're dealing with. There's this first variable which says unnamed. I think this happens if this is just the index which was not named, so it is imported as an unnamed variable. In Python, normally the rows have labels, and those labels are supposed to be that's supposed to be the index, and if the index has no name, it is imported as unnamed. So we shall drop this variable because we don't need it. The next point, we drop the variable, and then we can now see the first variable is here, and the last one is this timer. We have dropped the first variable, which we don't need for anything. So the next thing we shall do is check for missing values. So this command checks for missing values. It gives you the list of the variables and number of missing values for each variable. And you can see the departure time has 8,255 missing values. So missing values for departure time could mean a number of things. Probably the flight was cancelled, most likely. Then the delay in arrival is the total of 9,430 missing values. This is a little more than the missing values in the departure time. So these are the number of missing. So delay in arrival could mean 2 things. Either it may be some of these that never departed, so they never arrived, or the flight could have been diverted to some other destination. The tail number for some of the planes are missing also, and the time in the air is 9430, which is the same as the number of those missing values for the delays in arrival. So the ones that never arrived at that destination also are missing the amount of time that was taken to fly, the duration of a flight. So as it is, there's not much you can do with these missing values. You can't replace them. You'll just have to work with the data as it is. Now you can also get summary statistics. So this first one here, I don't know if the font is too small. Let me try to enlarge the font and improve visibility or legibility. Now, this command gives you the summary statistics for the categorical variables. You can see in here we have asked it to just pick out the categorical variables, and these are the ones: carrier, tail number, and so on. It gives you the count, the count of the non-missing values. It gives the number of unique values. So there are about 16 different carriers. The tail numbers are almost 4,000 different ones, and so on. Then the top means the most frequent one. So the most frequent carrier is UA, and it appears 58,665 times. The same applies to us, but this is just for the category. If you want to get the descriptive statistics for the numerical values, I think you'd have to change this to np. Is it number? So then it will run the statistics for the numerical values. For some of the numerical values, it doesn't make sense. Like year, month, and day, we don't need, we may not be very interested in the mean, say, for the year. In any case, it's the same value throughout. But values like departure, variables like departure time, departure delay, and so on, the time of arrival, the distance, and this may be of interest. It gives us all these summary statistics: the mean, the standard deviation, the minimum, the quartiles, the median, and the maximum value. So again, this can be a quick way to see what is in your data. It may not be very easy to digest when looking at figures like this. But if you wish, you can select a specific variable and focus on that one. Or you can also just generate statistics for a specific variable, in this, which we shall not do for now. So we'll start doing some exploration. The first thing we shall look at is try to analyze the flight delays. So we're trying to find out which airlines have the most delays. So the first thing we do is the airlines have been in the file. There's this short names for the airlines, but we want to be able to see the actual names of the airlines. So what I did is I created a dictionary here which gives the actual names of the airlines as the values and the short names as the keys. And then I use that to create a new variable, which now has the actual names and not the short names. So I will if you run this, it adds a new variable to the. You can see we have added a new variable, airline, with the actual names. Okay. So now when we run the analysis, we'll be able to see the names and not just the short names. So the next one is we group by airline, and then we just get the count of the number of times the airline appears in the dataset, and that will give us the count of the number of flights by the airline. So this may include even the cancelled ones and so on, because even if it's cancelled, it is listed there. So if you run this, now we get a bar. This is the one we saw in the presentation. You can easily see which airline had the highest number of flights. And you can see SkyWest has very few. I think it's quite hard to see that here. So if you wish to, let me see, we can change the scale of the x-axis so that it's easier to see these smaller values, but then you will lose the actual count. You'll just be seeing the relative difference between the different. You would have to change the scale. Let me see if I can do that. So we want to change the scale. So we shall use the log transformation to change the scale. That might help with the visualizing. Yeah, now you can see the smaller values are easier to see. But now the scale is no longer the actual scale, but transformed to logarithms. But then you're able to see these small values that were previously not visible. And you could easily have thought they were almost zero, but there are some flights from this airline, SkyWest airline. So this one was just the counts. The next one we ran is still a bar plot, but what it's showing now is the average departure delay by each airline. So this shows the average departure delay by each airline. Now again, you can see if you keep this as a vertical bars, you have problems because the names are really long and therefore it's hard to read. So a good idea is to flip the coordinates so that the airlines are on the y-axis, and then it will be easier to display them. I think the next chart does that. It puts the airline on the x-axis and gives the average average departure in delay time by airline. So again, Frontier Airlines, was it again? Frontier Airlines seems to be the one that has the highest average number of delays. Or average, highest average number of delay time in minutes, not delays, but the highest number of average delay time. So I don't know whether they are not as efficient as the others. United States Airways or US Airways, I think, has the lowest average value in terms of delay in departures. So we can also visualize the delay. This one simply gives us a point estimate of a value, the average delay time, but we can get a distribution by using a box plot. So when we run a box plot and we distribute this by airline, you can see the United Airlines at the top. So this gives you a distribution. You have a few outliers. Then you have the median and the mean, the two quartiles, the first and the third quartile, then there's a median in between. These ones on this end are outliers. So this is actually showing the actual values of the delay time in the departure for each flight, for anything that is beyond this threshold up here. So these are what we consider outliers. We have some extreme values for each airline. Let's see. There's one airline here which doesn't have a lot of extreme values in the delays in departure. And there is SkyWest down here, which does not have any extreme values. They're just all within 200 minutes. So 200 is the number of minutes. I mean, what is the delay in departure is measured in minutes. So 200 here means minutes. But what it shows is that there are some that are really delayed by a long time. These are 1,200 minutes. Now, to do your analysis, it may make sense to have a cutoff so that you don't work with these outliers. The outliers can skew the analysis or even further visualization. So now we try to look at a few more dynamics. We want to know if evening flights have more delayed than morning flights. For that, we create a variable which is categorical with two categories, morning and evening. Morning will be between 1 a.m. and 12. That will cover morning. All the other times will be classified as evening. You can change these values to suit what you want to get. And then when you get the average values, it seems the evenings have a higher average value. In terms of delays than the mornings. Mornings have 24. Now, the only problem we have is here we have included even the ones where the depart, no, we have removed them. Where the delay in departure was less than 0. We have removed them at this line, so they are not there. So we have only included planes that actually delayed, where the delay in departure is greater than 0. Where it's less than 0, and there was no delay, we have left them out. So this covers only the planes where the planes that actually delayed. So on average, the evening ones have a higher average. The morning ones have a lower average of 24 minutes. I think it's easier to visualize this in a bar plot. That's what we do next. So you have the bar plot. And for the bar plot, it's clear. The evening has a higher average delay than the morning. So this may be useful to whoever is in charge. So we can check the distribution of the flight delays. You can use there are two things. You can use a histogram and a box plot. We use them concurrently. So the histogram shows you this data is skewed to the right. So the lower values are more common. And this one clearly tells you that this being the third quartile, this bar here is the third quartile. This may be around, was it 120? I'm estimating that. So this may be around 120 or thereabouts. I'm using that because I'm thinking in terms of hours. So that would be about 2 hours. So this is a third quartile. It means 75% when of the delays are less than at most 2 hours. But then you have some delays which exceed that value. These are the outliers. So we can also just extract the top 15 delays if you want to see the extreme values and where they belong. So we have listed the airline. You can add more variables if you wish to get more information, but I picked only 2 variables, the airline and the departure delay. Then we've listed the top 15 largest delays. So the highest is about 1,300 minutes. The one at number 15 here is about 849 minutes. This is the delay in departure in minutes. So this gives you the actual value for a given flight. So you can locate it in the data frame using the index. The index value is here. So you can get a better grip on how the data is distributed. The quartiles give you a fairly low resolution of the picture. You can get percentiles. The percentiles now are a bit more refined. So for instance, the 10th percentile will give you the point for which you have 10% of the data below that. Usually you have to order the data and then you can use a percentile. So if I run this, you can see that 10% of the delays are 2 minutes or less. 20% of the delays are 5 minutes or less. So, and if you go down, you can see that 95% of the delays are 148 minutes or less. You can go up to 99%. You may go higher if you wish, but 99% of the delays are 252 minutes or less. We could use a bar plot to do this, but at this point we realize we can work without the outliers. So we could choose to cut off everything that is above the 95%, above the 95th percentile, and then work with that. So that's what we do next. We remove everything above the 95th percentile. And then when you now try to visualize the shape, I think it looks much, it's much easier on the eye now than when you had the outliers. And it also shows the distribution. And now it's, in this case, once you remove those ones, it shows you that out of these ones, about 75% are less than 100 minutes, the delays. This is the for this streamed data, this is the case. So you may be also interested in seasonal trends. There's a column for month in the data which we can use we group by month and then compute the mean delay in departures. Again, we focus only on the planes that actually delayed. And then when we draw a line plot, which gives us the average for each month for all the flights. If you wish, you can do this for each airline. This does not distinguish between the airlines. It just captures all the information. But if you wish, you can do this for different airlines and analyze them separately. There's a lot of messages in the chat. I don't know if there are questions. Maybe I can look at them as soon as we are done. So this tells you again the average delay seems to be higher in the middle of the year. So there's a package called Plotly, which can sometimes be, especially if you want to do dashboards. We have produced exactly the same graph, but now we've made it interactive. So for this one, you can actually, the mouse can activate these values. They are displayed when you point at the marker, you see the value. So this one tells you the month is January, and it actually gives you it gives you the exact value for the delay. And for the other one, you would have to guess. Either you guess, or the other option is to put the grids. You could put the grids. Let's see. The grid will help you if. So if you put the grid again, it can help you guess the values to some degree of approximation. But if there are no grids, you can't. But for this is good for dashboards. But if it's for printed reports, it won't make a big difference. So this is easy. If you can, I think it can be also saved as an HTML file, and then it can be viewed on a browser. So for anyone who wants to see, they'll be able to pick out the values just by running the mouse around the values. So here we have done this by month. The next one is we pick by the hour of the day. And when we run that, you can see, so this first one is 1 a.m. The average delays for the flights that live between 1 a.m. and 2 a.m. I think this is for 2 a.m. Now, apparently there are no flights departing at 3 a.m. and 4 a.m. because from 2, we move to 5. So the ones that leave at 5 a.m. seem to have a fairly low average delay. The ones that leave later in the evening, it climbs up again. But the ones that delay most seem to be the one that are in the wee hours. The average delay time seems to be higher for those planes that leave in the wee hours. So you can also do the same for quarters. In this case, I used the Matplotlib. You check the average delays for each quarter of the year. The first quarter, second quarter. Of course, we had to introduce a new variable to take care of that. I'm trying to. So we also check by days of the week, which days seem to have the higher. Again, Thursday and Friday seems to have a higher average delay in departure. In the next one, we do that separately for each airline. So this enables you to analyze the airlines. But something interesting here comes up. There's these SkyWest Airlines. They don't seem to fly on Tuesday, because there's a gap here. Apparently, they don't fly on Tuesday. So we can check which airports have the worst delays. There are only 3. So these two, LG and EWR, are not too far apart. JFK has a slightly lower average departure delay in minutes. So this is the average. And then remember, we are working with we have removed the outliers. We are working with a data set that doesn't have everything above the 95th percentile has been kicked out of the data. So this simply counts the number of flights by quarter for each airline. So you have this is there are 2 things happening here. You have the cross tabulation. The cross tabulation now is then converted into some grouped bar charts. Each group is for an individual airline. So for instance, this group is for the American Airlines. The blue bar shows the number of flights in the first quarter. The orange one is the number of flights in the second quarter, green third, and the red is the fourth quarter. That is just for this. Now I'm looking at Delta Airlines, sorry. So this this, you have the count on this side. Again, you see the airlines that have very small values are not visible. Again, you can change the scale. If you change the scale on this time, we change the scale on the y-axis. We make it a log scale, then the visualization is improved. Because now we're able to see the smaller values. But again, like I said, what has changed? Oh, I need to say Y scale. What have I done wrong? Yeah, I did not specify the transformation. So I'll specify the transformation. Now, if you now you can see even the ones that were really small are visible. So the scale has changed. So this doesn't give you the correct comparison in terms of the differences, but it gives you the relative. It still retains what was high remains higher than the others, but the difference now is what you can't tell easily. But you get the relative change in values, and the visualization now is improved. Of course, you gain something, but you lose something as well. Another way also would be to make this airlines on the y-axis, because they are long labels, you can put them on the y-axis. The next one simply gives a histogram of the distance covered by the aeroplanes. We saw this in the slides. The next one is a scatter plot of the distance covered and the arrival delay. Then we've covered it by the colored using the departure delay. So this, we have a legend here which tries to indicate the colors. I don't know if, I can't remember what's supposed to be used. Let me try this. The color map seems to be not so good. So if this doesn't work, we'll just let it go, but I don't remember the keyword for this. There's a keyword for changing the color. We will. I'll just leave it as it is. But if you change the color, you will be able to cover to observe the differences better. So the color is by the departure delay. The graph shows the delay in arrivals versus the distance covered by the aeroplane. So you can see even for short distances, you still have some, I think, and here we picked only the planes. This condition here ensures that we picked only the planes that delayed in departing. So you can see some delayed in departing but still arrived early. You can see the ones that are negative, the ones whose arrival delay is below 0. It means they still arrived early, even though they left late. Oh, is that the case? Yeah, I think so. So the next one also is a scatter plot, just checking on the arrival delay and the departure delay. We saw this in the presentation. You can also try to extract the top 10 most popular destinations. So this destination ORD, I'm not sure what that stands for. At about 17,283 flights going there. It's the most popular. At number 10 was DCA. Number 9 was MIA. I think MIA must be Miami at about almost 12,000 flights going there. You can view that better in a bar chart. I think this bar chart is too big. We can make it smaller, but it's easier to view. Yeah, so this is easier to keep track of than the table that we just looked at. So this clearly shows this airport had the highest number of flights. This destination. Their destinations are many, so I've only picked 10. There are more than 10. So you can also check the flight routes. So you have the destination here, and then the origin, and here you have the average delay in departures. So for instance, the flights that came from this EWR airport headed to this destination, which is TYS, on average, they delayed by 77 minutes. So on. So the next one simply counts the number of flights delayed, giving combinations of the origin and the airports. So you have the 3 airports here, the destinations, and these values are the number of flights delayed. Where the 0 probably, it either means they were not, it could mean 2 things, either the flights were not delayed or there are no flights from that airport to the given destination. So here maybe I'll need to label this, but I picked the 5 largest values from this JFK airport. So, and all these are flights that delayed. I think we picked the ones that delayed. So from JFK to LAX, the highest number of delays, it had the highest number of delays, about 4,084. And from JFK to this destination, SJU, I don't know the actual names. These are the short forms of the names. They are about 18,000 delayed flights. So this is similar. We're just doing this now a pivot table. The one we did earlier was a cross tabulation. This is a pivot table, which now the statistics in here is the average delay in flights. You can change the statistic to something else. If you want the standard deviation, if you want the median, you can change that as well. So I think that's the end. There's a lot more you can do with the exploratory data analysis. I hope this has given you a rough idea of what is possible. And at least the ideas are quite intuitive. They are not complicated ideas to comprehend. And that brings us to the end of the talk. I don't know if we can get some questions, or maybe we should check the chat now. So there are a few questions about outliers. It depends on what you're doing. There are cases where you can drop them, or you have to drop them, or where it makes sense to drop them. There are cases where you will have to retain them because they add some value to your analysis. You just leave them as they are. There are cases where you'd have to replace them with other values. You impute them, just replace them with other values. Or sometimes you replace them with missing values. If you don't want to lose a lot of your data, the outliers can be treated as missing values, especially where it's clear that they don't make any sense. They can just be replaced by missing values. So there's no one size fits all when dealing with outliers. And depending on what you want to do, sometimes you can transform your data. You can leave the outliers in and transform the data so that their impact is minimized. The impact of the outliers is minimized. But that would probably be another class on its own or another presentation on its own, just to talk about what to do with outliers. So there's no one size fits all solution to outliers. You'd have to take it on a case by case basis. Seems to be the only question.
I'm trying to get a hand up, but I cannot see. So my name is Benson Agaya. I have a question. I see some of us may not be so familiar with the notations. For example, when selecting the set of variables to run to see the to do the visualization. How do we go about this? I saw you tried one a while ago. For example, coloring and all that, or distribution, how the line, which ones would go into the line graph and so on, or histogram. What is the way forward on annotation?
Now that one, if you already have some experience with Python, maybe if you have the script, it will make sense. If you are new to Python, you may need some training in Python first before that can be solved. So like the training we have in mind will be a little more intense. It will run for 3 days in about 2 weeks. And there we shall cover the details of Python.
All right.
Now here it may be difficult to explain everything. It takes a bit of time. If someone does not already know that, it takes a bit of time. So, but this script will be made available also. There are a lot of resources also online. If you want to just learn Python, there are a lot of free resources online. You can, for me, I learned most of it from datacamp.com. I also, there are some books. There's a book I've shared there on the references. That's quite a good book to learn Python for data analysis.
Okay.
The presentation will be shared, and maybe you'll be able to access the title. And then, so the only solution would be to have a separate class for coding. Then we can go through the details. It's not possible to cover that in the same 1 hour. It's quite challenging to do that.
That's appreciated.
But if there is interest, maybe later on, we can try to have a class where we have, we try to have a crash course on how to do some of those things. We could pick a small topic, like not really small, a small area in visualization. Then we focus on that and do something like a 1 hour talk on just visualization. That would mean a live demo. It will mostly a live demo or a tutorial, if you like, for visualization. That can be done. So someone is asking about the code. I have not shared. Yes. So the code definitely needs a few more comments. I have not put enough comments. Some you can put yourself as you go through the code. Any insights that you gather, you can put as comments. So I have put a link to the notebook. that has the code. The data will be shared later, but if you'd like, you can go to R, and in the NYC flights 13 package, you can load that dataset, save it as a CSV file, and then you'll be good to go. You'll be able to work with it. So, Kelvin, you have a question?
Yes. Thank you, Professor, again for this. I think this is the first session that I'm joining, but I'm seeing there's a lot of insightful information. What I wanted to ask is creating a production tool from this insight. Let's say, for example, you want to create a dashboard, not a dashboard, but let's say a feature or a tool for the, should let's say, for the airlines or somebody who needs this data for decision making. And what I wanted to ask is how can we go about it, or like what tools do we use so that even as I'm following up and looking at what you're doing on the collabs, should let's say I have, should let's say, an end goal, for lack of better words, so that I can I have a project base, so that at least I improving on it, because it's very interesting, very insightful. That, and I believe, okay, I've gotten a little bit ahead of myself. The previous question before that, question number one, that is question number two, was how often is, from your experience, how often is this information usually needed by the whatever party that needs it? How often do they, let's say, is it usually every quarter, or let's say, now, if you can give just a couple of cases, and then now, if you will indulge me, you can maybe answer the second question now on how the production pipeline or production tool now to serve those people who usually need it is typically done. Thank you.
Okay, thank you for the question. That's a good question. This one was mostly set up for teaching purposes. The setup is not production; it's for pedagogical purposes. Maybe optimized for that. But if you want to, you can have this on a dashboard. Now, how frequent do they need this? This was static data. All this data is for 2013. So if you have data that is being updated frequently, like daily, you may need to get daily updates. It depends on your domain and what makes sense for your domain. So if you need it updated daily, then they can check daily. For instance, these are daily flights. So if someone was monitoring this, they would probably need, across the year, they would probably need daily information. And then you can still split it. You can still have the daily information and still have the quarterly or the weekly or the monthly information. All that can be made available. So you can pick what makes more sense at the time you want to check the updates. There's one interesting one which is updated. I think there's an API you can use to get all the flights that are in
Yes,
the air.
I believe it's Flight Radar or something like that. Flight 24, Flight Radar.
Okay, that's what you get online, but there's something you can run in Python. There's a package you can use in Python to extract live data for airlines. You may not get all the same information as we have here, but it will just tell you where the location. You can even now map that data because it gives you the location, the latitude and longitude, and you can it is updated every 60 seconds, so your map can be updated and so on. I don't have time to cover that now, but there is an app. If you are interested in something that is frequently updated, that would be a good project to do a dashboard, and then you can keep monitoring the flights, those that have arrived, those that are still flying, those that are, and so on. Hopefully, I'll try to organize more talks and cover some of those things. So, Victor Otieno?
Thank you so much, Doctor, for this class. This is very insightful. What I just wanted to inquire, I've been running my Python scripts on Jupyter Notebook, the Anaconda. What I wanted to inquire about the Google Colab. You said it is free. For how long can you run data using Google Colab? Because sometimes I see there are some charges when you use some other Google platforms. Is this free? Can run as many data as possible?
Yeah, it's free, but I think if you may be limited in amount of if you want something very heavy like these neural networks that require a lot of data, it may not work, especially like if you're working with satellite images. They require a lot of CPU time.
Okay.
For that, you may need to buy. You may need to pay. I'm
Okay.
using the free one.
Okay, thank you.
For that, you may need to pay. I have never used the paid one.
Okay.
So I don't know how that works.
Okay. Thank you.
But you can also change. You can get some limited time. Like if you can change the runtime type. So you can see, but you may get limited time. Some of these you can see are not active. So maybe those I need to pay first before I can use. But I have a GPU here, which I can use. If I have some heavy analysis to do, I can use that. But then I may have a limited time on it. I've not tried this. The GPU will do some heavier processing. CPU, what we are doing now is comfortably covered by the CPU. But if you have a very large data set, maybe, or something that requires a lot of computing time and resources, the GPU you may need to switch to GPU to run it. I think the rest you have to pay for. You can see they are not active.
Okay, thank you so much.
Any more questions? So I will hand this over back to Henry so that we can conclude. And thank you very much for showing up.
Thank you so much, Dr. Katende. And I trust everybody had a very wonderful and insightful course today. The recordings for today will be uploaded to the Google Drive, which the link have shared. And also I'll be sending you the same link via email and also a registration link for our upcoming course on the next 2 weeks. So I hope we'll see everybody there. And we'll also be having the final series next week on Thursday, same time and on the same link. So thank you all and have a blessed day ahead.